Just for reference, here's how you solve that on the Macs, that problem we were having where it doesn't want to start. Here's one workaround. There's a path to where Jupyter Notebook config file lives. And you can put that line in there which says, rather than try and figure out which browser to use, it just opens it in Safari.
Yeah, I'm seeing a notebook for your thing instead of.
Because that's John's screen.
Oh.
So we're going to switch back in just a second. This is just for reference here.
Do not put Chrome in there. As I mentioned, Chrome has another break. So Safari or Firefox.
Isn't it great when computers are just easy?
Mm-hmm.
I was going to try Mosaic.
All right, come on. There we go. All right. My screen still sharing, Pete?
It just shows a picture of you right now.
Okay. Come on. How about now?
Yep.
All right. Now we all got a nice food coming going. Time to start diving into some Python. So I want you to go back to your notebook main page here. We want to go to the primer directory. And under primer, we're going to go into this notebook called primer. So the idea here is to go over some of the more just beyond beginner parts of doing Numpy and Matplotlib. And then we'll also cover doing some calculations with Metpy. So just to have an idea, who's never heard or never used Matplotlib or Numpy? Okay, gotcha. So we're going to start here by looking at index and slice arrays. So with Numpy, its big claim to fame and the feature it provides for using Python is the n-dimensional array class. So that provides a way to wrap a homogeneous collection of items in memory that are contiguous in memory and be able to slice and dice and do mathematical operations on them. So the first cell I'm running here, is that big enough? Probably not. How about now? Good enough from the back? Okay. And let me there's no way to hide the rest of that, is there?
Yes. View. Or window. One or two. Window. Oh, hide status bar.
All right, that'll work. So the first thing we run here is this import numpy as np. As John alluded to earlier, that's kind of a standard convention when working in Python, is to import numpy and shorten it to just np dot. This is a way to keep things short and sweet, but yet you can still identify what functions in your code come from NumPy, which ones come from Matplotlib and whatnot, without having to type numpy dot whatever. It's only saving 3 characters, but we'll get to some more kind of conventions like this where the savings are significant. Okay, we're going to create a sample right here for working with it. We're going to run numpy a range, get its numbers from 0 to 11. So we're going out to 12 here. And then we're going to call reshape on that to give us an array with 3 rows and 4 columns. So we can run that cell and then look at the output. And so we see we get 0, 1, 2, 3 in the first row, 4, 5, 6, 7 in the second row, 8, 9, 10, 11, third row. So if you're not familiar, indexing in Python is zero-based, like C, how it should be. And so this command below, we're going to look for index 1, 2. So that is the second item along the first dimension, and the third item along the second dimension, which is second row, third column. So second row is this row right here. Third column is 6. So if we run that, we should get 6 out, and we do. Of course, with NumPy, one of the nice things is you don't have to give it necessarily an index for every dimension. You can just give it one particular. So in this case, we can just ask for, it'll default to the first dimension when you give it just a single number. So in this case, we're going to ask for the third row here. So a square bracket 2, we start at 0, 0, 1, 2. So it's the third item, third row. We don't give it any indices for columns, so it'll give us the entire row. So if we go back to our original here, A, the third row is 8, 9, 10, 11. So that's what we expect to get out here. And lo and behold, it works. Another nice part of NumPy then is that you can use negative indices to count from the end. So instead of having to sprinkle, at least last time I used MATLAB, this was the case, having to sprinkle end or length of a particular dimension or whatever hard-coded number throughout your code, you can just say -1, and that will give you the last entry along a particular dimension. So A 0, -1 should be the first row, and then the last column. So again, going back up here, first row, last column, should be getting 3. Anyone have any problems with that so far? Okay. Next, we move into slicing. So if you're just using a single index, you're just pulling out a particular entry along a dimension. Slicing allows you to pull out kind of an ordered collection of one or more entries. So we write these by talking about where do you want to start? Where should we stop? Just specified as really one past the end. And that works nicely with start by the number of items is just stop minus start. That's kind of why they index like that. And then you can optionally give a step factor so that if you want to say count every other or every fifth or whatever, you can use the stride to kind of say how far you should be jumping from that to get each successive item. And then you don't have to write all these in Python. But you can leave out the step and it'll default to stepping by 1. If you leave out the start, it'll default to 0, so it's the first item. If you leave out the end, it'll go all the way to the end. And we see the syntax here is written as start, then stop, and then optionally, if you want to specify how big your step size is, another colon, and then the step size. So start, stop, step. I know it's a little abstract to be talking about this way, so let's go through some more examples of how this works. So I'll put up the original array here. So that's what the data we're looking at. So now we're just going to give it a slice along the first dimension, 1, 3. So that means start at 1 and go up to 3. So it gives us 1 and 2 because it'll stop before it gets to 3. And that goes along with, so 3 minus 1 is 2, so we should get 2 items along that dimension. And so that should start at the second row since we're counting starting at 1, and gives the third row at 2. This next one is an example of giving it, we call it empty slice, just a colon. So then using just that colon, Python will fill in the default start and the default end for you. So it'll start at 0, go to the end. So that just gives you all entries along that particular dimension. But by doing so, that allows us to write then colon comma 2 to say, give me all rows and only give you the entries in the third column. So going back to our original, all rows, third column should be 2, 6, 10. We can achieve the same thing by replacing that colon with a dot, dot, dot. Except for that dot, dot, dot could actually be any number of dimensions that it needs to fill in. So if this was a 4-dimensional array, it would pull it in 3 empty slices and then index along the last dimension. It's a useful trick to have if you want to write code that can handle a 2-dimensional array, as well as 3-dimensional array, as well as a 4-dimensional array. If you're working with gridded model output and things like that. So a nice little trick to have in your pocket if you need to work, make more generic functions that can work with any array you want, as long as all you care is to do some operation along the last dimension.
So that command, if it was 3-dimensional, would have dumped out?
Would have dumped out the third item, all leading dimensions, so all, I don't have good nomenclature for a 3-dimensional array. We'll say row, column, depth. So it'll give us all rows and columns at a depth of 3. Or the depth of the third item along the depth dimension, so index 2. Or if you think of this as time, z, y, x, all times, all heights, all latitudes at longitude index 2. That one. So here's an example of using the strides. So here we do colon, colon 2. So this is going to fill in. I'm going to default start at 0. Go to the end. This time we included the stride, so it's stepping by 2. So we're going to start at the first item, skip the second, and go to the third. Only for the rows. We're going to get all columns because we didn't specify any index along that. So that basically is a quick way to get you every other row. Just count by 2s. So every other row, we start here up top. Should get the first row, 0, 1, 2, 3. Skip the middle one, then 8, 9, 10, 11. We can do the same thing and combine that with the empty slice for the rows to say, give me all rows, but give me every other column. So if I go back up here, I want all rows, but every other column. So I should get the first column, 0, 4, 8. Skip the second column. Grab the third column, 2, 6, 10. And that's what comes out. Anyone have any thoughts on how you would do every other item along both dimensions? Anyone brave enough?
Colon, colon 2, comma, colon, colon 2.
So like that. Is that what you're thinking? Okay, and that should give us first row, every other column, so 0 and 2. Skip this row, and then give us every other column from this row, which is 8 and 10. So 0, 2, 8, 10 is what I expect to get out here. Real quick way if you're plotting to decimate, downsample, skip items, whatever, when you're doing a plot of maybe wind barbs or something, and you don't want every wind barb. Quick way to say, give me every other. Or you could put, if you have maybe a conus her run or something, and you just want, downsample maybe 10. You could do colon, colon 10, colon, colon 10, and it's a quick way to then not have to deal with every data point. So that was NumPy indexing. I want to move on now to Metpy, which is a library for doing meteorological things in Python. That can be reading some of our funky data formats. That can be a lot of meteorology-specific calculations, a la the GEMPACK grid diagnostics, trying to fill in those. Also include some of our peculiar plotting things like station plots, SQTs, things like that. One of the things for using calculations, Metpy is based around having unit information attached to your arrays of data. It makes things more verifiably correct, helps prevent a lot of weird unit errors, helps prevent having to sprinkle manual conversions of Celsius to Kelvin to Fahrenheit and back throughout your code. And it saved us a lot of effort on documentation of saying, thou shalt put density here in kilograms per meter cubed. This one takes mixing ratio in, needs to be unitless. That's kind of an easier one, but for making sure that potential temperature that you put things in, right, you can't take Celsius, it has to be in Kelvin. So it saves a lot of those challenges. So to work with the units, we do this import. We say from metpy.units. So within Metpy, there's a subpackage called units. And from that, we import the name units. And that's what we call a unit registry. That just has all of the various units that are available within there. That's actually from a package called Pint. It's a unit library for Python. So we import that, and then we can start working with units. And so for instance here, I'm going to set this variable length and say it's 8 times units.feet. And that's all it takes to attach unit information is simply multiplying by it. So say 8 times units.feet, we get length in feet, and then we could say print length times length to get the area. And it handles keeping track of what the appropriate units are for that calculation. So we get out what you would expect, feet squared. We can do a little more here and say, here's the distance in miles. Here's the time in minutes. We can calculate the average speed using that. So the average speed is distance divided by time. We get the average speed. We see originally it keeps things in the original units here. So 10 over 15 becomes 2/3, but it leaves it in miles per minute. Not always really what we want, so we could say, hey, take that average speed and convert it down to the base units. And so then that prints out, it gives us back to SI, so it gives us meters per second. Of course, here in the US, what we really probably want, is miles per hour, at least sometimes when you're more easily trying to think about things. So we could say, average speed, give me that in MPH, which Python understands as miles per hour. And so we get out 15 minutes, or 10 miles in 15 minutes is 40 miles in an hour. So this fits in with Metpy because we can use its library of calculations with these units to do things in a robust and straightforward way. So for instance, we'll start here and we'll say, I'm going to make some random data representing wind components, UNV wind components. This first line here is just setting a fixed random seed so we all get the same values. We say, give me a random set of integers, give me 10 of them in the range 0 to 45. And then I'm multiplying by units m/s. So earlier we did things by saying units dot mile. So you can chain together that. We could do units dot meters divide by units dot second. That is one way to write it out. Or a shorthand. Python is smart enough to parse this, so we can just give it a string with a unit expression in there of m/s, which we'll interpret as meters per second. So here we go. We have 2 sets of wind components with units meter per second. Yes.
So is there a way to look at the options for average speed .2 so I can see what all the different kilometers per hour, what the syntax would be? I tried to do tab, but I don't see where I get
You get
.2.
2, and that's about it as far as the valid units. As far as the strings, I can understand the abbreviations. Well, let's see. Hold on. Before I see something on the turn here. So if we do units dot tab, that's where you can see at least all the valid units that it supports. So let me see if K. Okay, so KPH is there. So that's usually the way I'll go about it is use the units dot and do tab completion on it. Now that's only for ones where it basically has a registry of units and someone's manually added that abbreviation for kilometers per hour. There's no way to get to know that you can understand that. So that's, if you're going to try to do the expressions like that, you've kind of got to go to the point of look up KM, which will be in there, and HR. And it also has full understanding of various prefixes and things like that. So it's got a pretty wide gamut of things.
Just about everything you could ever want is in Pine. I mean, furlongs per fortnight works as a speed.
So is the .2 method?
Yes. And he wasn't kidding.
Yep.
Furlongs per fortnight is a valid thing it will do.
Horsing around.
All right. So I can run that cell, get my random U and V win components. We can print them out, and we see we get some values here. And it's got the unit information when we print them out. Meter per second. So here's another one of these shortened imports. I'm going to import metpy.calc as mpcalc. Again, I'm a lazy typist, so.
Just a quick question. Theoretically, every time I would submit this command random seed, it should give me a different outcome.
If you didn't set the seed, it would give you a different outcome. Because in that cell I set the seed, I am returning the random number generator to the same initial state every time. So we import metpy.calc as mpcalc, and then we can use mpcalc has get wind speed and get winder functions, so we can use those to get the speed and direction corresponding to those wind components. So I can run that to get speed and direction. Excuse me. And so if you don't get an error, print out the speed, we get these various speeds. It says meter per second for the speed. And then we get those for the wind directions with units of degrees. Of course, one of the nice things is for many NumPy functions, the units just pass through just fine, and the mathematical operations hold on to the units. So for instance, we can take the average of those speeds using np.mean and print that out and see we get the average speed with the proper units attached. Same thing also works if we want to do the mean and maybe standard deviation of the wind direction. Maybe if you're doing some kind of windrows or something like that. Of course, wind direction's fine, but it's not as, that one's a straightforward calculation. What about something like calculating dew point from relative humidity and temperature? Metpy calc has that in there. For some reason I've duplicated the import here. But we could say we calculate the dew point and relative humidity. We calculate the dew point from the relative humidity. Temperature is 25 degrees Celsius. 0.75 relative humidity. Now if we run that, we see the dew point's 20 and change with proper units attached. Nice part is the calculation works just fine if you give it degrees Fahrenheit. So same calculation. 77 is 25 degrees. 77 degrees Fahrenheit is 25 Celsius. So if we run that within the few tenths I was rounded here, we get the same value here. And so if I save TD here, and then I can say, hey, give me that back so I can have the dew point degrees Fahrenheit instead. We can get it back that way. Metpy also has a large collection of various constants that are useful when doing meteorological things. So we can import that, metpy.constants as consts. And you can actually use that question mark trick that John showed you earlier in the notebook to bring up the docstring for that. And it doesn't show up really well when I've zoomed so far on the web page, but I'm sure for you guys out there, you get a much more readable table listing all of the constants, their names, the symbols, as well as short names and what their definitions are. All sorts of things like the Poisson exponent, the kappa, dry adiabatic lapse rate, epsilon for mixing ratio. All those constants are available in Metpy already with units attached. So to say we want the density of liquid water at 0 C, and get constant density water, and that prints out 1,000 kilograms per meter cubed. Or for kind of something that reads a little bit shorter than density water, we also have it under abbreviated as rho_L. So far, so good. All right, let's stop listening to me talk and have you guys do something. So if we go back to the primer directory here, so I went back to this main notebook tab. We have the list of notebooks. We'll go down to primer exercises. We have this notebook here with exercises. So we're going to do exercises 1, just this, the ones under exercises 1, these 3 questions. So use Metpy calc pressure to height STD function, calculate the height of the 700 millibar level, assuming a standard atmosphere. Calculate the wind chill when the temperature is 263 Kelvin and the winds are blowing at 20 meters per second. If you want bonus points, try and do that 28 degrees Fahrenheit. And then using the values in metpy.constants, let's figure out what the dry adiabatic lapse rate is, which is G over C sub P D. And we'll take about 5, maybe 10 minutes to go through that. And so you'll have to go through the process of importing the right libraries and running the calculations and use things like the question mark and whatnot to bring up the docstring to figure out how to use these things properly. Try and start getting comfortable with how you might use this after you leave this class. It's not bad. Not bad at all.
I think we should reframe the year examples always. Airspeed velocity about like 12.
Laden parcel.
neglecting effects of coconut and everything else. I feel like it's more appropriate use of Fairlight for Fortnite.
It's the airspeed of nothing. So African European. I don't know.
Undocumented. Maybe under window. I was trying to remember.
There's something somewhere that'll let me do this.
You're in full screen, right?
I am in full screen. Is it here?
Do you hide tab bar?
It won't let me hide the tab bar.
Always show toolbar in full screen. That one's unchecked.
Ah. Let me go back there and see if we can still read that. Just one click out. Basically down unless you're ready to move on.
This is like that. Wait, what is a millibar? It's like 1/1000th of a bar.
Cross-sectional
Who does
M bar
M bar.
or HPA.
Oh, I did try
HPA. So,
It doesn't like HPA.
Are you
I did that. Can't repeat it work.
It's not. Okay. Case matters. Just like we want. All right. Thank you.
I want to convert it to that. Which it seems to understand that all these images are objects. It's like,
you get a bunch of
I mean, it's carrying around the
so it's not it's trying to convert.
oh, I also have that.
So what do you use for this? You import. It's a good note for NumPy. I give you a name, NP, like a namespace to access. So pressure type, STD, find the Let's say I have 700 meters. So instead of M, I'm on M bar. So you're not saying, no, you're saying there, you're giving it a value. I have 700 something. In this case, you're saying 700 times. So I have 700 millivolts. Convert that to a hyper vector. In this case, that function is this function. M bar. MB ends up being some weird. B is short for some SI magnet. M bar or HPA. Okay. I don't know right now off the top of my head. It's way too quiet in here. By all means, cheat off your neighbor. All right. Sure. Okay. So to convert, we'll use .2. You use times to kind of attach new information. You use .2 to say, you can't use closer than 4. So 2 parentheses. One more parentheses. And it needs to be units that thing. Okay, so that one, that import line, the units import line is slightly different than what people go back and look when we get to the see how I imported it as that. So from Matplotlib, import the name units.
Oh, okay.
So that's what the problem. All right. It's a little tricky. I can't. So if you do that, I think otherwise that will work just fine.
Oh, yeah, okay. First I wanted to go with this last time.
All right.
So here, I'm using units dot.
Sure.
So here I'm using units parentheses. Why would you use one like that? Because in units parentheses, HPA doesn't matter.
Huh? Oh, okay. It needs to. So I bet PA works. So if you only use 70,000 PA would work. So in that case, I would use parentheses because you want the parser. You want the parse that expression. I wonder if I should just add that manually. That's probably a good thing for my part of view.
So this is how I would do that?
Actually, if you're gonna do the parentheses, you can just put the HPA. That'll work. Yeah.
Yeah, so maybe I didn't.
don't know if we're going to have 70,000 text.
Well, yeah.
So the parenthesis one parses it, and it does all this stuff, whereas dot notation is just whatever objects are predefined. And clearly, it doesn't actually have the predefined HPA in there. It just has, it knows about pascals, and it knows about the prefix H. And so the parser can put that together. But nobody has said HPA is this particular unit. But I'm thinking that I should add that.
So units dot HPA, I mean, that doesn't work.
Does it? Oh,
Yeah, it does work.
I thought it did. Okay, never mind.
So units, but units dot
It may be
Yeah,
something.
yeah.
Is it .k?
Mhm.
Okay. So I thought it was dead K, which was an abomination. Dead K? Right, but not exactly. That's like, yeah, that's an abomination.
Degrees Celsius, but Kelvin's is
But I think dead K works.
dedicated words. Backwards compatible. Back to Python 2.7.
So only time I use the parentheses one, the quotes and all that is when it saves me typing, like for m/s. Things like that, where I can write a short little expression that would otherwise be units.m/units.s. That's usually my line. If you get into long things like meters per second squared or something, you can write something much shorter in that little parser than you can in Python code. That looks good so far. Oh, the units. You need to import the units. So if you look back in the primer,
If I do something weird, I get this, which is
there. So you need to import the units registry so you have access to units. Yep. If you print height, you can see what that is.
Let me see if I can reproduce that. You can convert meters to mega.
here.
Okay, that's okay. Now what happens on the next one?
I mean, this is, okay, so it's still a meter. I don't know, that should be like trivially reproduced.
Yeah, please do, John.
Yeah, I'm gonna try
I
right
mean,
now.
that's not Metpy's problem, but I will report that, that's for sure.
That's something that needs fixed.
And it should raise that.
It absolutely is. I have no problem getting it to raise dimensionality at most times. The fact that that one doesn't is weird.
Yeah, I can do it. And I have no idea. It's using 1,754 as the conversion factor. I have no idea where it's coming from.
It doesn't need it in a particular unit. It just needs, here you're saying the 700 millibar. You change the units, then you're changing what the value is. So you're giving it a different pressure value, you just change the units. No, because that's what it uses pipe for, just to any pressure value. So it's just kind of fall out naturally. So basically, because you have millibars, that function knows how you convert the values. Yeah. Yeah.
Their interface looks very much like mine.
Sure.
They have their own.
Sure. Well, 700 pascals is way up high in the atmosphere. If you change it to 70,000 pascals. So then you get the same answer.
Yeah, I was somewhere on that subject. I always learned about these things like various project that uses astro
Extra Python units.
I mean, it's kind of a larger general question. Other big code base that kind of follow around up with this sort of nasty bug because the library that silently took. Well, yeah, I think actually like return non. So it's like how consistent is the quantity? Something that
Yeah, it's tricky. It's something. Discussion I'm trying to push.
There's some bugs in Matplotlib where everything should work nicely used, some things don't. I'm gonna file a log in our issue tracker, and then we can figure out where it lives. It's gotta be fine.
Replace from Metpy units, import units with, yes, import pint units equals pint.here.
Because I can reproduce and it has a constant of 1,754 as the conversion factor.
I don't, it looked to me like it just treated it.
I mean, they have context in their places where you can say, we should convert this because we should be assuming a wavelength of blah, 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 or something. But
That's a serious thing. Also,
yeah, no,
Question just, is there, can you use the question mark kind of tip in order to find out what the streams are actually needed by?
He said, I'm not seeing the top sheet.
Okay.
No, that's not what I thought it was. Okay, so this is totally rework on it.
Yep.
So you want to use not this.
You did exercise two, too? Oh, no, just the first step.
Are we supposed to do the heat index?
all right, no, just these guys.
So this is the first three.
Bang, bang, bang.
Okay.
And yeah, green stickies if you are ready to move on.
So Ryan, oh, did you just
Yep.
reproduced it?
Yep, no Metpy involved, all pint.
I'll go file it.
Final one pint. That's bad. Even if there's like some context where that makes sense, it should not be on by default. No.
Yeah, that's bad.
Bad pint.
It's
Your
famous,
AOS
yeah, so that
Python
too.
thing just went out.
Oh, did it?
Yeah.
Oh, goody.
So,
What just went?
My blog post for AOS Python.
future AOS Python.
Is it this H Greco fine? Oh, no.
Did you spell it right?
I clicked the link.
What?
This is, you know, Johnny one. Says
Oh, good. GitHub's having problems.
this is it.
Yeehaw.
What
What did I say this morning?
Hey, we got a clone. We're good now.
You don't have REOS, but you
Not your AOS.
Yeah, even Unidata Metpy is dead.
Woohoo! No, just like type one. So there's those three pressure to height, wind chill, constants. So when you're done, the green comes up.
Well, it seems something, I think it's screwed to.
How's the stock?
It's still down.
Oh, that makes, I can see where that might creep in. It shouldn't, but I,
Like I randomly
Throw
pick
some sheets.
other things. and it's like allowing it
well, I was thinking it was a setting Metpy thing, but we did it without Metpy. So it's a default bug in there still. That's well, the reason we use Plank is because it actually has support for real temperatures. There are several other libraries out there that handle like delta degrees Celsius just fine.
Oh, that's what they're gonna do.
We need absolute temperatures. Python does an AstroPy. I haven't checked it out. I was kind of reticent to say Metpy depends on AstroPy. That was.
Yeah, so I can convert Teslas to temperature. So.
Oh, fantastic!
But they all use that same 1,754 constant.
Oh, great!
So, Teslas, seconds, yeah, anything goes.
I bet 0.7 doesn't. I bet it's probably 0.8.
No, one day I'll check.
So that's supposed to be like that. So.
Yeah, yeah. It's not, but it doesn't have a,
It should follow the whole
doesn't have a, what do you call it? It doesn't have a visual, it doesn't have a screen on it. People were speculating on the screen.
Maybe there's a screen if you like.
So if you do NP calc that wind chill question mark, make a new cell and do that.
Precision acoustic forms, direction control.
Okay. Temperature, speed. Okay. So that's right. Now, why is it? I'm just trying to get an extra now.
There should be coffee coming with the break, whatever time.
Kelvin, okay. Try not capitalizing it.
From vending import coffee.
3:20, I think, is when break is supposed to.
And then you might want to take out the question mark.
Just want to make sure we didn't hear everybody in here.
I don't think it's here yet. I think they're bringing it in time for the break. I think. I haven't looked at it. Maybe you're.
All right, 2 more minutes and then we'll move on. Fine bugs in the
I
workshop.
appreciate this.
Yeah, Vic Royal, love it.
I was going to show colored barbs on QT, but
No, you're not.
that's not it.
No. We haven't cut a release because it wasn't worth cutting a release for.
There is coffee and cookies and stuff next door, so if anybody wants to go grab some.
I keep going.
Okay, so hold on a minute, and we'll go. Exercises on the 20 minutes.
There's coffee and cookies and stuff next door if anybody wants it. Yeah. And yes, you can have food and drinks in here, just try not to spill. This is our undergrad sports with our undergrad, so
Now it becomes unheard of.
people, it's had its share of food and drinking here.
All right, so going through these exercises. So the first one, we need to import unit registry, import metpy.calc as npcalc. And so npcalc.pressure to height std 700 times units dot mbar or units.hpa would work. That's that one. npcalc.windchill 263 times units dot Kelvin 20 times units parentheses m/s, and we'll go ahead and find it in Fahrenheit. And then the last one, import metpy.constants as consts, const.g divided by consts.c sub pd. Oop, what did I do wrong? Capital C sub pd, or CP_D. That was my thinking on those. Anyone have any disagreements with those?
We just did a lot longer. A couple more lines.
Nothing wrong with taking more lines. I've been doing this a while.
I just keep trying to tell you
Yeah, someone found that last time. I still haven't fixed the exercise.
So, I was just curious with the Metpy calc.
Mhm.
Is there what, like, if I didn't just, I was really didn't know what if I wanted to put the wind speed before the temperature or something like this, how do I know what
Sure.
variables in the
So best way to do that. So I've opened up a new cell here. MP calc dot wind chill question mark brings up documentation for that. We see doc string and the calls right here, temperature, comma speed. If you don't like that, I'd show you the docs, but I think GitHub's down. So, you know,
GitHub is down.
GitHub is throwing 500 errors right now. So
Yeah.
if GitHub was not throwing 500s, I'd show you our beautiful web documentation where you could also go and find outside information. But alas, the benefit of the question mark works offline or when GitHub's down.
So I did searches on Google and I found the references for the values,
Mhm.
not examples of the syntax. Is there?
We have some examples. We tend to do those for plots and longer stuff. We don't have an exhaustive set of examples for them. Actually, if I'm thinking about this right now, what I would probably do is I'd like to have examples within here, because you can do that within Python in the documentation, example calls. That would be a nice thing to have. I don't want to snarkily say pull request welcome, but we should add that at some point.
Into the Metpy documentation?
Yeah.
I think GitHub's up.
Is it now?
GitHub's back.
Oh, okay. So if you go to unidata.github.io/Metpy, you get Metpy's web documentation. So there's things for install guide, a little bit on our unit support. You have the examples, which is a gallery of various graphical examples, or at least they tend to be plots of using these things. And so you can click there, get syntax highlighting images, and then you can also download these as both the Python file and as Jupyter notebooks. And then over here under the Metpy API, excuse me, all of the subpackages are documented. So if you look at metpy.calc, here's a table with all of the functions. And so we can come over here to wind chill. And so there's also the web documentation. Sans example. So if we were doing our job completely right here, there should be some syntax highlighted code here showing how to use it and what comes out.
So generally in these numeric functions, you give the number times.
Yep.
Almost always the rule.
Almost always a rule in doing it this way. In my ideal world, you could read in a file and it will automatically attach the unit information since NetCDF data we frequently use has unit information. There wouldn't be that manual step. Alas, we don't live in my perfect world yet, so a lot of the time you're going to be saying multiply by units. Okay.
So, I mean, similar to what I was talking to you before, if I am going to run a quantity through something and it needs to be an array, what's a plain array? What's the way to convert back?
I believe this was in our notes of things we should fix for this workshop. It didn't get done. My bad. So the one thing, I don't have any of these saved. Let me go back to my primer notebook since we're going there anyways. So there we go. I have So I have TD. And so if I do td.magnitude, that's how you strip away the units. You can also use .m. That's a shorthand for it, but I've been reticent to use that because it makes the code. It's easier to scan past a .m versus .magnitude is like a big blinking red flag of I am dropping units here. But that's usually the hammer to apply when this thing won't work with units. Any other questions on that? We're over time right now, just to be clear, right? Okay. All right, so next thing I want to show before we move on is a little bit more advanced NumPy indexing things. So we went through basic indexing, went through slicing. NumPy can also both create these arrays of Boolean values, so true or false. And why you might want to use those is because you can use those to index into a NumPy array and pull out values of interest. So what I'm going to do here is create some random data. I'm going to be a bit more fancy than just random integers as we did before, and I'll make something that looks like a realistic temperature and wind speed trace. I don't want to get bogged down in the details of all the NumPy calculation there. But if we plot up what I generated there, here's our trace of temperature and wind speed. And we'll do some more plotting after the break. Just have this picture in your mind as we go through the next parts of the code here. So NumPy supports comparisons between an array and a value. And what that does, just like if you have an array plus a value and it's going to go over each value and say, add this value to it for each item in the array, the comparison works the same way. It's going to compare each value against, in this case, we'll say, compare it against 45 degrees Celsius. We say temp greater than 45 degrees Celsius, and it'll return an array where whether it's true or false for each value in the array. So a bunch of trues and false, because if we look up here, 45 cuts across through here. And so here it's true at the start, and it goes false, and then it goes true. The reason you might want to do this is because then you can pass that as an index to an NumPy array, and it will only pull out the values where you have true in the array going into it. So here we're going to print out temp, and we're indexing the temp with temp greater than 45 degrees. So if we print that out, we see we get all these large values and nothing less than 45. You don't have to just do it with, itself. So we don't just have to have temp indexed by temp, but as long as you have a true or false value for every value in the array you're indexing, you can use any array. So for instance, if I wanted to pull all the temperature values where the wind speed exceeds 10 meters per second, we can do that. So for instance, here, I'm going to make a copy so I don't modify the original data. And here I'm going to say, with that copied data, set all the values where the wind is less than 10 meters per second to this np.nan. That's floating point notation for not a number, which a lot of packages, including Matplotlib, can handle as a missing flag. So in this case, if we do that and plot up the results, we see we get this temperature trace, which with these various values cut out of the trace because we set them to nans. And of course, if you really want to extend this, you can write basically, this is almost the equivalent of kind of an SQL database query here, where we can say where temperature is less than 45 deg C and speed is greater than 10 meters per second, give me the temperature values. If you're going this far, it's important to note that you must have these parentheses. Otherwise, the order of operation dictates that these two are going to get stuck together, and that ends up with a really confusing error message, and you end up Googling it, and eventually you find a Stack Overflow post that says, here's your solution. So if you're doing these, trying to combine Boolean arrays, make sure you have parentheses around these parts of it. So that's indexing with Boolean values. Of course, if that wasn't enough, you can also index a NumPy array with an array of integers. So for instance, here we go back to, I'll index with a single integer. Print temp 0. I get 69, 89, blah, blah, blah. I can also get the first, fifth, and 10th elements by giving it a list of numbers here. So I can say temp 0, 4, 9. And it will extract those 3 items for me. There are a lot of tricks that can enable. The one I want to call attention to here is NumPy has a built-in function called argsort. So if just sort will sort an array and give you the values in sorted order. That's nice. That's useful sometimes. If you use argsort, what that's going to do is give you the indices that would give you the data in sorted order. So we can run that. We get a list of integers. So now if we just pass, so we got this list of integers, or an array of integers, so just indices into the array. We could take temp and pass it that array as an index. And so now that gives me the values in sorted order. So we start at the bottom, 28. We see everything's increasing as we go forward. The reason that becomes more useful is if you want to sort one array by another array, that's how you can apply it. So if you had an array of date times, or if you wanted to get the winds corresponding to the temperatures in sorted order, or if you want to basically try and combine things from separate arrays, arg sorts your way, you can do that. So you can get the list of indices corresponding to sorting by time, and then pass that into temperature to get the temperatures in proper time ordering. Problems like that. Of course, we could also slice indices here. You know, say, so this is putting everything together in one last hurrah here. So we could say ins -10 colon. So start 10 items from the back, go to the end, take those indices, and then pass it to temp to get the 10 highest temperatures. That's how that generally goes. I know this is a fire hose of information. I don't expect anyone to take all of this away and be able to use this the first time. A lot of this is, now you know it exists. Now when you go and try and solve some problem using Python, maybe it sticks in your head, oh yeah, I remember there's some way to do this. I at least know what to look for. Or you can at least go to a mailing list and say, I know this exists. How do I go about doing it? At least you know the tools that are out there if you don't readily know how to use them right away. Okay. So I think for the sake of time, I think we'll skip exercise 2 for now. But let's break for 5 minutes, get up, stretch your legs, clear your head, because we've been in here, a solid hour. And then we'll come back here and we'll start on opening some Netcdf files and plotting out the data.
I think the use of argsort is to sort something, do calculations on it, and pass the indices back to the sorted one to get back in the original order. I do that trick a lot.
What?
So you get the
Yeah.
Like, and if the calculation needs to happen in order, like it's an interval pressure or something, and then I want to get them back.
It can't be.
If you pass the indices to the sorted array, you get the unsorted array back.
I don't believe that.
No, try it.
I don't.
It works. I've done it.
What's that?
If you use argsort and you get the indices,
Yeah.
you pass that to the unsorted array and you get the sorted array. If you pass those indices back to the sorted array, you get the unsorted array.
I'm not recording, so I'm not going to say what I'm really thinking. But All right, fine. So you say.
My favorite use that nobody else does.
I had to laugh when he said that. I don't expect you to remember all of this, but just, someday maybe you'll be like, oh yeah, that's exactly what I tell my students when I teach my intro to Unix class in the fall. It's like a 2-hour long, here's everything you know about Unix.
I know it works, but some of our code uses it.
The hell it does. Zip does that.
We use it somewhere. I've done it since I got to Unidata.
I'm sure that only works in certain cases. There's no way that can work in the general case. Oh, wait. Hold on. I bet you mean this.
Yes. Okay, there we go.
That still didn't work, but that's closer to something
So-
I expect to work.
Make like temp2 equals temp ends.
Nope.
But don't compound.
I see, but I see where you're going now.
Yeah.
But you have to change the indices too,
Yes.
and that's. Yeah. Okay. Now I'm with you, but I'm still not sure where we're using that.
There was something where we used is interpolate, because in interpolating you have to have X in increasing order.
Oh,
I
well,
want to pass back the array in the same
interpolate's black magic.
order they gave it. So I sort it, and then whatever interpolate gets back, I do the reverse sort. Also, look at our website. I post 2 things.
What?
So, 1, in here and out here are tinged different color. You can see the div. And 2, there's a 1 pixel offset between these divs,
Ah.
and now I can't unsee it.
Just go point it out to Doug. Then he won't be able to unsee it either. You evil, evil man.
Also, I'm on the website here for half an hour.
So like for the second exercise, I was just going through it.
Sure.
Does the heat index, does that use a lot of like masked where type stuff or masked array type
It
stuff
use-
underneath? Or
Yes, it's that Boolean indexing stuff.
Yep.
It's doing that exact thing on the.
Okay. Okay, thank you.
Come on, Mountain Dew.
Yeah, you don't want to do this. This is just gonna quick jump.
Oh yeah, I've given up on that stuff. I'll go chemical rather than carb. Do. Oh no, not more.
No, this was the bug that this other project had, and they're sort of the same
Oh
thing.
yeah. That sounds like. Yep, that'll do it.
So I don't know. I mean, this is maybe arguably a NumPy problem.
Well,
Why does it?
The reason is because the first thing it does is going to take those arguments and it's going to call np.array on it, and that's going to shed units instantly.
Right, but I don't understand. Like, why does it collapse the -1? That's weird. Because if it
That
just-
is. Hold on. What?
right. It's,
Huh?
it's worse than you think.
You're right. Did it? He? Oh dear. Oh. I'm sure there's a rational explanation behind what's going on, but it usually takes walking line by line saying,
Yeah.
that's terrible.
Anyway, that's why. Well,
NumPy random uniform between 0 and 9, 3 items, proper values. NumPy random uniform, if you go between 0 meters and 9 meters, you get an array of -1s, which doesn't look like it's even running the random number generator.
no. Oh, and there's sometimes these like subtle issues. To be honest, stuff like this makes me a little bit reluctant to like leap to use units everywhere, because it's like
I agree.
even though there's
Oh,
huge advantages to doing so.
Can you put the unit thing on the outside?
you could. Yeah, that's how you would
Should
end
there
up
be
solving it.
a three dot? Should there be units on the increment?
No, because
No.
that's the shape of the array.
Yeah.
Oh, shape of the array. Okay.
So it has nothing. There
Okay,
should be
yeah,
no
yeah,
units.
I agree with you 100%. Units has been the most controversial and pain in the butt thing I've done in Metpy. And the only thing worse than using Metpy's units is tracing through every
Well,
calculation
I
and
know.
figuring out, do I have proper units? Otherwise, it's a pain in the butt
Well,
because of things like that.
I mean, it's a pain, but like the payoff is like potentially.
Well, and then hopefully eventually we just fix those problems and get units done right in the stack. Basically, there's a lot of discussion that maybe units should be able to be done through the D-type.
Yeah, it
And
probably
then-
should get pushed upstream.
Exactly.
NumPy.
And then, or at least the talk I've heard is make NumPy's D-type more customizable. And then you use a custom D-type with unit information attached. And then in theory, everything just works. But
It's more, well, it's not gonna just work, but the right people are there will be like test cases.
there is no silent losing of the D-type.
Well, and someone would write a test case.
Exactly.
Well, I
Yeah, that's
know
his-
this was the error that
it's
this other
terrible.
project had. So if you run it through the uniform, it's put unit. So they had the same problem with AstroPy. So, this just silently makes another array of the same shape. So your code doesn't fail.
Thank you for giving me another slide in my SciPy talk. Yeah.
So,
I'm giving a talk on how much of a pain in the butt units is in Python, and it shouldn't be. Like, Matplotlib has support for units.
Yeah.
Should be able to just use plaint. Nope. All right. All right, looks like we got everybody back. Let's start moving on. So I'm going to close out my notebook. I don't know if John showed this earlier. I don't think he did. But if you want to close a notebook, you can close the tab. But if you want to shut down what's running, you can go to File up here in the tab bar in the notebook and say Close and Halt. And that will both close the notebook tab and shut down the Python kernel that was running behind it. File, close, and halt. So now we're going to move on, and we're going to go up to this notebooks directory again, add a primer. So click notebooks here. And then we're going to go down to this time series directory. And we want to open up this notebook called time series plotting. So we're going to walk through over the next hour or so how to open Netcdf files in Python, pull out some of the data out of them, and then plot that data, or really it's model output. So plot that output using Matplotlib and make some nice looking time series graphs. So who's never heard of Netcdf? Never. Okay. So Netcdf is a binary file format that is we call self-describing. So as opposed to having fixed these bytes need to be this and then these bytes are this field, Netcdf provides a binary file format with a library behind it that allows you to encode arbitrary n-dimensional array data in a file. In addition to the n-dimensional array data, you have attributes attached to it, as well as attributes at the global file level that allow you to store metadata about what's in the file. That can be who created it, that can be units on particular fields within the file, things like that. So quickly here, what a Netcdf file contains is you have groups that can logically arrange the file content. You have variables that store the actual n-dimensional arrays of data for all sorts of different data types, including 1, 2, 4, 8-byte integers, 4-byte, 8-byte floating point data, strings, and then with NetCDF4, you have support for what we call compound types. If you know C structures, that's essentially what's going in there. If you don't, if none of that sounds familiar, don't worry about it because compound types are a pain and you really only need them if you really need them. Otherwise, let's stay in a nice world where it's just an array of floats or integers. You have dimensions. These are dimensions. A dimension is a size of a particular dimension along the ND array, and these are shared between the variables so that you can reference things together. So for instance, you have an x dimension, and you have the actual x coordinate values along that dimension, and you have a y dimension and the y values along that, and then maybe you have an array of temperatures, which is laid out along the x and y dimensions. And they all share those common dimensions to make it easy to plot up and work with the data. Or say you have temperature and dew point and pressure. Those all share the same dimensions. That's one of the things that NetCDF adds on top of, it's actually based, NetCDF4 is based on HDF5, and that's one of the things that adds to HDF5 is this notion of sharing dimensions between variables. And then lastly, we have attributes, which store metadata, units, long name, descriptions of what variables are, conventions followed in the file. Any number of attributes or metadata that you want to store in the file, you can encode as attributes, which again have the same notion of different data types. The traditional library for accessing this is the NetCdf C Library. And if you've ever tried to do it, accessing NetCDF data in C is an utter pain in the butt. I mean, it's nice compared to having to write your own file formats for some things. But since C is a statically typed language, trying to work with arbitrary floating point or integer arrays becomes a bit of a hassle in C, and just you have a lot of code calls, so it can be a bit verbose. Working in Python, however, with NetCDF is much, much simpler than C. And we'll see how this looks in just a second. Been a lot of different libraries that have worked with NetCDF data, especially the NetCDF3 format, or a lot of different Python packages that handle that format. For NetCDF4, the predominant package is NetCDF4-Python, written by Jeff Whitaker at NOAA's Earth Systems Research Lab in Boulder. And so that's the library we recommend. And should Jeff ever need to step away from the project, somehow we'll find a way to make sure that keeps going, because NetCDF is one of the things Unidata, where we work, makes. And so it's important to have good Python bindings to access it. So to start off working with NetCDF, first thing we want to do is we're going to import from NetCDF4, import data set. So that's the overall, it's a class, and that's how we start accessing NetCDF files in Python. Excuse me. And so what we're going to do next is we're going to say GFS data equals data set, and then we just give it the path to the NetCDF file. So here I give it a relative path from the notebook to a place in the repository you cloned with some sample NetCDF files. I hold on to that reference here in GFS data, and I print it out. And we see we can get a bunch of top-level information about what's in the file. So we can see things like the conventions and the history to see where the data came from. We've got the list of dimensions here. We've got various variables that are in there, such as convective available potential energy surface and convective inhibition surface and temperature surface and so on. If we want a little more information about what's in the file, we can take GFS data and look at the variables Python attribute here. So GFS data dot variables. What that gives us back is a Python dictionary. So if you're not familiar with dictionaries, it's Python's probably predominant data structure that maps one thing to another thing. You've just got these pairs of items, a key and a value. In this case, with a netcdf file, the natural mapping is the string name of the variable, and that maps to this variable object that gives us access to the a particular variable within the netcdf file. So if I just print that out, I get this big ordered dict with information about all the variables inside. So if I just want to, instead of seeing all that gobbledygook, I just want a list of the variables that are in there. So for that, we say list. So that's making a Python list. And I can just give it the dictionary here. Say GFS data.variables. And that converts the dictionary to a list. It just pulls out each of the keys and gives you a list of them. So that's how we can see what variables are actually in the file without having to trace across with our eyes all that other junk. And we just see there's temperature surface, isobaric 3, U component of wind isobaric, relative humidity isobaric, and so on. This is actually converted grib output from the GFS. So that's where a lot of these kind of awful names come from, is how the grib variables are defined, and trying to make unique names programmatically from those various grib variables.
Any error messages there?
That's not good.
You have to make sure you run each of the. So.
If you want to make sure you run all the cells, we can go up to here. I'll do this for mine here, so I'll make sure. You can go to cell, all output, clear. Now all my output's cleared. So now I'll go back down here and I'll run so I can see that I've run each of these. So for that, if I went too quick there, it's cell, all output, clear. And that's how you can wipe all of the pre-saved output from the various code cells.
So the list show that all the variable name inside that netcdf file.
Yep. Well, that's a generic Python idiom for taking a Python dictionary and making a list of the keys. That just so happens that with a netcdf file, we readily get a dictionary mapping variable names to these handles, essentially, these variable objects. And so we can use a list just to get all the names.
Question. You generally would not load a netcdf file into a Numpy array.
You won't load the whole netcdf file, but what you will do is, we're going to go through here. You can index into a netcdf variable and get out a NumPy array. So you very much are still working with NumPy arrays. You just have a couple of steps before you get the data as an array.
You generally read netcdf into a dictionary and then you may extract it.
That's what the netcdf library is doing for you, yes. So now I can dig out one of those particular variables out of the file. And so that's what we're doing here is we'll say temp var equals GFS data dot variables, and then in square brackets we give it temperature underscore surface as a string. And so that looks for a variable named temperature surface and returns you the metadata so far. One of the important things to note about netcdf here is, so far we haven't really done much in the way of I/O. It's read a few kilobytes of information off the disk, but we've not pulled all of the binary data on disk into memory. So if you have large netcdf files, say 20 gigs of a climate model or something like that, you could still just open the file here and you haven't done an excessive amount of memory usage so far. That only happens when we start trying to pull out the data from the variable. So far here, all we've written is metadata, no actual data itself yet.
So the current shape is the size.
Yes. So just like a NumPy array, you have the shape information. So if we look at this variable, we see information about the data type. It's 32-bit floating point data. Here are the dimensions it's a function of. Here are the units, the long name, standard name, various just high-level information about the data that's stored in the file under the temperature surface variable. So far we've looked at how variables are mapped, how the Python API handles variables. And you just have this kind of natural Python mapping of using a dictionary to map variable names to getting information out of a file. Attributes work the same way. We just take the GFS data we opened. So for instance, if we looked up here, when I opened the file, we printed it out, we saw all these various attributes that were defined on the file. If we want to access those in Python, we just take that GFS dataset object, and we ask for the Python attribute conventions, and that gives us the netcdf attribute from the file. Same thing works for a variable. So up above, we have the temp var variable, and it has an attribute called coordinates. So if we ask for temp var.coordinates, we can just pull out that information about that particular attribute. So if we want to look at, say, the shape of a variable, does anyone remember how to do a shape of a NumPy array? What about the number of dimensions for a NumPy variable? Not dims. Size is the total number of entries. Ndim. So just like a NumPy array, netcdf variable provides the same set of attributes. So tempvar.shape gives us a shape, and dim gives us number of dimensions.
So the way the dimensions are laid out in netcdf, does Python flip those dimensions at all?
No.
Okay.
Matches. They're both C
So
ordered.
like an NC dump on the netcdf file or something. So what you see, so like say XYZ would be XYZ the way Python reads it.
Yes.
Okay.
Okay, so again, so far, all we've done is metadata. We've not done any kind of reading of arrays. Now, this is a small file. There's not a lot of data in there, but on a big set of model output, this would be a significant savings so far as you can do a lot of queries without doing a lot of I/O and without using a lot of memory. So now let's actually pull in the data from that variable. So we have this handle, temp var. That's a reference to the variable in the file. We're going to give it an empty slice, just like we did in the last section. And if we do that, now we've got the actual values from the file. Now it's actually nothing special here, but it's just a NumPy array. And from here, that all plugs in great with the rest of the ecosystem we've been playing with so far, and that we'll continue to be working with today and tomorrow. That's one of the nice things about this netcdf library is if we compress this down to one box here, we get about 4 lines of code to go from opening a netcdf file and pulling out NumPy array of data from that file. If you're doing this in C, this would probably be about 100, 150 lines of code. Especially if you're doing all the error handling properly. If you just want to skip that, you might be able to get it down some. But of course, if you had a big field coming out of a climate model, too much for one slice even to fit in your memory, you could still do a subset here when you're trying to get points out and not read in the whole set of array data. You could just ask for a subset of the data from the file, and it would only read those few values. So for instance, again, if I want to grab the first 10 values, so temp var, anyone want to venture how to get the first 10 values? Colon. Okay. What about every other point? Close enough, yeah. So, all right, let's print out one of these at a time. So there are the first 10 values. Oh, I hit this last time too. So it does not work like you expect. Very good. So it's a two-dimensional array. And if we do this, we give it 1, it's going to do that along the first dimension, which has size 1. And so it's not really doing any subsetting. So 0, colon 10. And then same thing here. I'll comment out this one and do this. 0, colon 2. So it works just like a NumPy array, but it is a NumPy array with 2 dimensions here. So we need to handle that first dimension, even though it only has a size of 1. I'd like to say I put this in purpose as a teachable moment, but alas, I did not. It's a product of how the files are stored. So now we can look at the time variable. Oh.
There's sort of like squeeze.
Dot squeeze. That would work absolutely. So if instead you want to do that, the one challenge here is squeeze is only available on the NumPy array. So if you wanted to do it only read in that subset, you couldn't rely on it. In this case, we have 24 total values here, so all of 64 bytes, we can read in the whole array. I guess 96 bytes, but bad computer. Uh-oh. Oh, there we go. Did I lose my stream?
Yeah, I think I lost you. You're still connected, but not full screen.
Of course. Come on. You can do it. All right. So, access temperature variable so far. Now we'll access the time information. So this time we'll get time var, GFS data variables time. We'll print that out. Okay, same kind of stuff. This time we have information about the calendar that the times are from, standard name, and the units. Well, this is interesting. The units on this thing is hours since 2015, 714, 0Z. Well, that's interesting. And if we look at what that looks like, we're curious what that looks like. Time var, empty slice, reading the data. So here are the times we're pulling out of the file, just floating point numbers, 93, 96, 99, and so on. Not particularly useful without doing a lot of thinking about how that references versus 2015, 714. So Netcdf for Python, fortunately, provides us some nice utility functions to convert these to Python date time objects. So if you're not familiar with these, Python in its standard library has a date time module that provides date time objects that nicely provide a way to work with dates and times. So for instance, I can, from the datetime module, import datetime, and this is how we can create a datetime object by hand. Just say datetime, the year, the month, the day, hour, minute, second, milliseconds if you want to do it. So you can do it by hand. The reason I bring that up is because we can use this from Netcdf for import num to date, and that's going to convert numbers to dates. And to do so, we start by giving it the values. So we take time var and give it an empty slice to pull out the values for times. And then the second parameter is the units for that time. So it knows how to understand hours since whatever, days since whatever, all these with their time streams that I believe are compatible with the UD-Units library and are used by the climate and forecast, or CF, Netcdf conventions. And so we can take that, We say times equals num to date, give it those two things and print out times. And we see now instead of 96 and whatever, we get something that we can glance at and see, okay, that's July 17th, 2015 at 21Z, July 18th at 0Z, 6, 12, 15. Much easier to make sense of than figuring out in your head what 96 hours since, pick a time is, what 103 hours since July 14th is. So once again, we come to time for you guys to do it and for me to stop talking. So if you go back to the time series directory on the main notebooks page, we have basic time series plotting exercises. And I would like you guys to do exercise 1. So there's another netcdf file in your repository called model-nam. Unsurprisingly, that is NAM model output. And then the goal here is to read the data from a particular day, July 19th, 2015, for any of the data variables in the file. So trying to put together some of the subsetting tricks. You can do this by hand just by setting fixed indices. Or if you really want to go all out, you can make date times and do the Boolean indexing tricks. You know, compare the date time against an array of date times and get the Boolean indexing, or you can just say, hey, give me the data from indices 8 to 15. Just the goal is to get an idea of how to index it onto that variable to only pull out the data for a particular time range that you're interested in. Either way, that will require using num to date to process the time variable data. Is that a good idea? Works for me. I like standing better.
There's no point where we can stack them. We should start writing it out and see how many people have never seen it.
Oh, you went on this. Live code on an overhead.
Syntax highlighting by these kinds of
No, thank you. You sure? Yeah, I'm doing all right. Well, no, I'll keep it.
all of that. I mean, if it was the past 5, but I don't think you're doing pretty good. I think somewhere between an hour and a half is the right amount of time for skis.
Is that one any better? Yeah, okay. I still got Mountain Dew.
Eric submitted the Matplotlib call because GitHub virtual PR and everything.
I'm proctoring your example here.
We're gonna miss it.
Earth Keep all hands meetings this week. Everyone's gonna miss it. No one's had the
Exam, I feel like it's a question I should just, sorry. I'm sorry. I'm afraid.
Of course, green sticky's down, and then put it up if you're done. But I'm assuming no one's actually ready to move on yet.
emailed you that GitHub thing.
Great.
I assume you were RMA at UCAR.
Very good.
I just grabbed it for pizza.
Okay.
Okay, all right, I'll see you tomorrow.
Yeah. Have a good one.
It's actually But then, I guess it's
So that's in right there. So then that's we import date time from the date time module. And so that's why its name looks like that in there. It's just a date time module dot date time. So what this is an example of just creating one by hand, a date time object. It's year, the month, the day.
So there's nothing really that it was.
It's just an example of doing it, how what date time is doing. And then here's how we use the utility from Netcdf Python to take an array and convert them. So we're making a bunch of these using that function Numpy.
Okay. Okay.
So if you can scroll up, taking that array of numbers and converting them to date times.
So that's the upper time.
Yep. So,
I'm not sure.
like in there, units, hours, since.
I'm just not clear exactly what we want what you want us to do.
I think you want to pull out the relativity, the added time based on the time arrays amount. I'm kind of stuck there too.
So.
Sugar coming.
So what I want is, let me go back to the, what my thinking is, okay, I've got this list of times here, right?
Yeah.
So if I wanted to say the data for the 20th, right?
0 or all of the 20th?
All the 20th. So if we look at times and say, okay, what's times? I mean, we do something really crude here and just say, okay, times 10. Oops, why can't I? Oh. Times dot squeeze 10, because I want to get rid of that size 1 dimension. Or I could just do. Okay, that's the 19th of 3, so maybe 15. Closer. All right, there's the start of the 20th. Starts at index 17. Then we're going to go to maybe 24, 23. All right, sure. So look at that. Figure out the times. I said the 19th on the exercise. So just figure out what indices you want to pull out. So don't just do an empty slice to read the temperature data. Use a particular set of indices is one way to do it. You could also go through the task of using the Boolean indexing and whatnot to do it without using a manual search here to figure out what you want.
Okay, yeah, I had forgotten the very first part where you said you wanted a particular day. So I wasn't here to see that either.
Note to self, put that in the comments.
I'm going to put that in the comments.
So that's
RTF MD.
Very good.
Read the fantastic markdown.
Oh, here. I want.
I'm sure you did.
Okay, so.
A spider in New Orleans.
Systems from one.
Oh, really?
He's making his way across the. That's what it's about. He's built that wall.
Procedure.
Is there a way I can access the individual days within the daytime budget? I'm thinking if I can be smart about it and say if that daytime, of the third thing is 19,
That day. I think
that day.
DAY. If I didn't tell them about time deltas, so they shouldn't need it. Shouldn't.
Something like that.
Did you file out your strategy? So how exactly am I getting to this?
You want to tackle that or something?
Yeah, but why?
That was here. That's the units.
Oh, okay.
Yes.
Sure. So, pull out the time. Yeah, so if you want to. Right. Exactly. So the key is to look at looking for time values using one date. Okay. 2 day times. And then the original intention was to look at those values and figure out should it be 17, should it be 19, 27. Or should be a slice. But if you want to look at and do a comparison, the last section, the temperature, really temperature against the temperature value, really values. Some kind of thing. Well, yeah, I mean, that's what we come out and do it that way. The only exercise was to try and get the line.
Let's just move to like whatever that is. Let's have the day, month, like a day or night.
You know what you're going for.
Because it comes up as like a ray.
Sure.
Year, month, day.
So instead of trying to plug in a month, make it be a time instance. Compare this.
Leave it in and then subset.
So
Subset. Subset.
And so put it area.
correct. By default, those are 0.
Do you want to know some time it's just 10, 17?
Yeah.
You understand?
Yeah.
Okay.
17 up to.
We don't even look.
Trying to be tricky and figure out the indices without, just from the time.
Right.
Feeling part of it.
Or 9 seconds.
list. Parentheses, my data variables. That's how you must do it. And if you run that cell, it's probably going to give you an error because I'm using square brackets instead of parentheses.
Okay.
That's always, you can't use my hand. It has to be and then you need parentheses. That's close.
After that command is set up.
Okay, I know a lot of you are furiously working on trying to get the bonus points and understand my confusing question. Just a couple more minutes and I will show you what I meant up there. So we can move on to the some more plotting type things.
I'm trying to figure out how you do how you extract everything with 19 out of this. I'm not getting this.
Yeah. You know, it still pronounces correct.
Sure. Oh, you need ledger. Actually, that should be good.
So it is the only one part itself.
Okay. So if it's by itself, it'll show it, but if it's in a string, it's not show it. So if I comment the other things out.
There's nothing after.
Is that just Siphon from bioscience?
So change all the AX dots to PLT.
It's plotting on a different figure. All right. So here's what I got so far. I've got my imports here from Netcdf. I have opened my file. I've grabbed the time variable out of the file. So I'm going to use num to date. Give it the values and the units. So now I've got an array of times. I'm going to pull out the temperature at the surface. We'll call you temp surface var for now. So far, so good. So if I just run that, I can look at times and say, okay, I've got, these values. Now, the real straightforward way, if we just want the data for 19 July, nothing sophisticated, just what is times 15? 0, 15. All right, that's close. Maybe 12. No, maybe 8. I mean, we're not doing, I'm not going for anything sophisticated here. Just it starts at 9. It goes to 17. Yeah, so we could do this with just temp surface var 0, 9 to 17. And if you're not sure about that, we can do times 0, 9:17, just to make sure everything's lined up. So those are the temperatures at the surface for 19 July 2015. That is the crude way of getting that out. Just playing with those back and forth. Now that's obviously brittle. If I want a different day, I've got to go back and do it. So the bonus points here was using the Boolean indexing. And so the magic here, I'll get rid of this, or I'll comment it out. We'll say, we'll just store this in mask. So if my range here is start equals date time 2015 7/19, end is date time 2015 7/20. And I need my date time import up here. And then we say, the values I want are times greater than start and where they're less than end. I guess greater than and equal to start and less than my endpoint. So that will give me a Boolean mask for all the times greater than, and then when you end it together with the ones less than, you get just the range you want in the middle. So if I want to pull those out, I say temp surface var want. Oop, what did I do wrong? Oh, so other hint, you will need to squeeze the values to a 1D array. So I'm just going to cheat and do 0, comma. I believe that'll work. Nope, it needs to be squeezed. Okay.
Indexing the times.
No?
Yeah, squeeze one, squeeze one.
Haha, thank you. There we go. So the problem was one ended up as a 2D array, which it doesn't like for using Boolean indexing. So we got our Boolean index, get rid of all this funky first dimension. And I think actually we could do this then. Nope. Man, I am just striking out today. All right. So that's the way to do it with it more programmatic, so that we can change just these date times. So if I just wanted the 18th, we change those two values, and now we still just get the ones we want. It's a good deal more complex and involves quite a bit more NumPy, but you know, if you want to go that far, it's available to you. So, any questions about that?
I've never heard of this squeeze thing until just today. So it means in one or two sentences.
Remove all size 1 dimensions. Because it doesn't, size 1 dimension does not affect how many elements you have. Anything else? All right. real quick now, so I don't take too much of John's time. We're going to get through here doing some plotting with Matplotlib. So we've read some netcdf values out of a file. We're going to plot them up. And so if you're not familiar with plotting in the Jupyter Notebook, first thing we're going to do here is this %matplotlib inline. This is a special command for the notebook. It's not proper Python syntax. But it tells the notebook that you should set things up so that Matplotlib plots appear inline in the notebook. So ordinarily with Matplotlib plots, they end up in a separate window alongside things, and you can close and whatnot. This tells it, make an image and just embed it right in the notebook. You lose the interactivity, but you gain the fact that these plots are now embedded alongside your code. When you save the notebook, they're saved out, and it helps kind of generate this document that contains prose, code, and analysis results. So that's what that line does. And then here's another one of those renamed imports. This one saves a lot of typing, and it's kind of a popular convention. So we import matplotlib.pyplot as PLT, and that shortens things greatly. So once again, I'm going to go through and pull out some data from the netcdf file. So I'm going to go back and pull out times. I'm going to pull out temperatures at the surface, and I'm also going to pull out the temperatures, which is from a fixed isobaric level. In the netcdf file, this comes out as a 3-dimensional variable with actually, 2 size 1 dimensions. So we just index them here, so we get things just one-dimensional arrays as a function of time is what we're getting at here. And then I also go ahead and can do the step here to convert that array of times to an array of date times again. So plotting. How many of you have not used Matplotlib before? Okay. So Matplotlib, go ahead.
Sorry, I was going to back up a
Yeah.
second. That's the very first line, times equals GFS data time, then you get 0 there.
Mhm.
That's 0. That's going to do what? Let's take 1, the first index.
Right, and so that first, so it's a 1 by 24 array.
Right.
So we're getting rid of that 1. Mainly because up to this line here is a netcdf variable object, which has no squeeze method. If it had a squeeze method, we'd probably just be using that and be done with it, but it doesn't. So we need to just give it an index there, and then it returns a NumPy array, and everything's hunky-dory.
So is this one of the things that Xarray deals with?
One of many things I think it deals with. So Matplotlib is a popular Python plotting library, and it has kind of 2 key top-level notions. It has what's called a figure, which is your overall plot that you are drawing on. And then it has, each figure has 1 or more axes, which is like an X and Y axis together, that you are actually plotting data on. And each figure can have any number of axes on it. Technically arranged arbitrarily, but usually you're kind of laying things out in a grid, because that's kind of the most straightforward way to get things. We're going to use this plt.subplots command to, in one fell swoop, give me a figure and axis. So by default, if we just call it with nothing, so just like that, it'll give us a new figure and a single axis on that figure for you right away. I go ahead and pass fig size and give it a size in inches, so a 10-inch by 6-inch figure, although not really because it's assuming 100 dpi display, which this is not. But really, this is just I'm passing a figure size so I get a bigger figure in the notebook rather than the default size, which is a little small for my liking. So that's what we're doing here. So this is give me a new figure to do stuff with, give me an axis to call plot commands on. Then from here, we're just going to plot. So we're going to say ax.plot, the times, the temps. We're going to make it red. We'll give it a label for the legend. And we'll call plot again with times and temps ISO, make it red again. We pass it a line style of dash dash, which means a dashed line. And give it a different label. We set the X label to time. We set the Y label to temperature. We set a title. Tell it to turn on the grid. And then we also turn on the legend and tell it to put it in the upper left corner. So if we do that, that's what comes out.
Why do you use subplots if there's only one plot?
So I don't like the PyPlot interface where you kind of have the stateful, you're modifying the current active figure, and you call plt.plot and whatnot. I like using the kind of object-oriented interface where it's you specifically say this axes should be plotting. So instead of doing plt.plot, I do ax.plot.
So can you not use ax if you don't use subplots?
So then I use subplots as a quick way to get a figure and ax in one swoop, as opposed to needing make a figure, add an axes, or plt.gca is another way to get an axes handle. To me, this is the cleanest way that, reads like regular Python code rather than MATLAB. But it's stylistic. Yes?
Yes, from the Netcdf C Library, you imported Numpy and data set. How do you know what we can import and out of it?
Reading the package documentation, looking at the examples, and you could do import netcdf4 and dir netcdf4. That'll show you a lot of things. The problem is you see some things that may or may not be useful. But that's probably, if that's what you're looking for, you'll see everything there unless it's a level deeper. But that's one way. So it was the dir command on netcdf4. So then one more here is I'm going to pull in, I'm going to open up that model nam file. Am I using? I don't know why that line's there. I don't think it should be there. I'm going to. So I'm here now at this one below my plot here, where I have all this plotting stuff. And I'm going to import some helpers from matplotlib.dates. So from Matplotlib has its own little dates module, and it has this date formatter and day locator. So all of this here is exactly the same as the plot we just made. It's the exact same, produces this, up to that point produces this. What I'm doing here now is, off of the axes, I can get the x-axis attribute. That gives me a handle to the object that manages the x-axis plotting. That's ticking, grid lines, everything to deal with the x-axis. To control ticking, Matplotlib has two pieces. It has what's called a locator, which controls where are you putting the tick marks in terms of how often are you ticking. Is it every 5? Is it every 10? Do I want the tick marks drawn at 1, 7, 25? You have that kind of granularity of control. What I set here on the locator is I say, give me a day locator. That's a special class Matplotlib provides. It helps it tick on the even days. To draw tick lines every day when you're doing time plotting. And then we also, when we're ticking, we have a formatter that controls the text that goes with each tick mark. So how do you want it formatted? Do you want it formatted just in scientific notation You know, with 2 decimal points, do you want it floating point? Do you want it rounding to the integers? Or in this case, we can use a date formatter to say label it with the month/day. So we noticed before when we did the plotting, Matplotlib did try and do something sane with the times we have, but we noticed it's 718 at 1z, and then 13z and 1z, which just feels wrong versus 0 and 12. That's kind of what we want. So here I'm just going to have it do every even day, and that'll get us close.
So if you wanted to have a tick mark actually every like 5th day, for example, if you have the longer time series.
5th day.
Or tick mark every day, but the date indicates only every 5th.
Say that last part again.
So you would have a tick mark on a day every day for 100.
But only every 5th labeled?
Yeah.
So notice it says set major locator and set major formatter.
Okay, so you introduce minus.
So we'll say day locator 2, which should do every other. The danger of live coding, but we'll see if this works. The 2 didn't do what I expected it to do. There we go. So it's interval equals. It's not just the default of the first argument, but it's interval equals 2. So that gives me, for the major one, locate every other day. And then you can set the minor ones to tick every day. So the answer usually to 90, we'll just say 90% of the questions, can Matplotlib do it, is yes. The question of whether or not it's easy to do or well documented sometimes is a little less positive. But you can pretty much do whatever you want. It gives you the wheels or the knobs to turn at some level in there. But sometimes it takes a little more digging to understand Matplotlib to really get there.
How would you, we're plotting the July, instead of doing 0, 7, how would you do 7, 19? Like, omitting the 0.
Sure. I will do that in a second, only because since we're finishing up here, let's go ahead and work on the exercise, which is go over to number 2 here and read in the data set, pull apart the data, and make a Matplotlib plot. Just like we did here, but do it with the NAM output and do whatever, Play around with Matplotlib a little bit and get comfortable with it, and I'll get to your question. Style and calendar should be links. All right, now. stringftime.org. Huh. Nope. That.
It must be the file.
Oh, it is. It's just. So to answer your question on the no zero, if you do -m, that gets rid of it. That's not guaranteed to work on all platforms.
Okay.
So otherwise, there doesn't seem to be an easy way to do it without doing a bit more custom code of controlling that.
It's a sign we're doing too much.
I mean, because
It's not bothering me right now. You have a good portion of the morning sometimes. I'm just fresh. Because I don't talk from like 3 hour block I'm off. So I'm all right now. My bad. It's too much material. I'm trying to get functional. I'm motivated. If you come and do something tasty, stuff and company does it, I could do 2 of our units. Oh, yeah. This is good. Thank you for my last time they were showing didn't have the address on it. Right is you have an umpire after that's first you do units. So that's what I'm saying. Okay. So you know, those are right. Well, outside. But to the right outside all brackets. It's only after that you get some material that actually have them top that. So first we would tell attention to our units. You know, just tell it times units is what we're saying. Or you could just do temp.I2, that would equal to in place two. Yeah, so rewrite this. That's what this workshop's good for, is if you're looking to schedule something here, and telling you in 30 seconds, or in 10 minutes. You're just going to put out.
Don't forget green stickies when you are ready to move on. Means my screen will stop shifting every time it saves. Because when the notebook saves, it comes on next to trusted. It takes up too much space. It's just not one down.
I don't have to actually change any function. It just hides it. Take a 10-minute break and I'll come back and go on to yours. So we'll go ahead and take a 10-minute break. Feel free to keep working, but we'll take a break. I'll show you my solution real quick, and then we're going to move on to John finishing up the day here. But now's a good time to stretch your legs and get your head cleared out. We're getting late in the afternoon here. I know I'm tired. Now what? I hate you so much.
I should do this.
It's not the same.
Oh, yeah. Not yoga?
That's not right. It's in your neighbor.
Yeah. Just broken. Yeah, I see me and
Oh, that's.
Yeah, that's interesting.
Mm-hmm. So buttons on the board. Wow. everybody back? All right, well, everyone's energetic right now. All right, so here's what I did for the solution here. I've got our set of imports that we've been working with so far. The only difference here is I have also grabbed this hour locator as well, and we'll see why in a second. Read in the data set. We pull in the various variables as well as the time and pull that apart. I think we've gone through that a few times. I also went ahead and I grabbed the height above ground variable. And I just want one of these. It's all the same across. So I'm just going to go 0, 0, 0 because it is a 3-dimensional variable with 2 size 1 dimensions, and the other one's all the same value. So I just want one of them. We're just going to pull that out. I went ahead and took the temperature value. So I've pulled in Metpy's units, and I attached the proper units and then used that to convert to degrees Fahrenheit. So I get my temperatures now in degrees Fahrenheit. Create my plot here, and then I'm plotting up the data. And so I take the temperature at the isobaric level, plot it up red, and give it a label isobaric. And then I'm doing the same thing here with the temperature at a fixed height above the ground, except I make it a dashed line. And then when I call label, instead of just giving a fixed string, I use Python string formatting and say, we'll make this at, fill in the variable here as a floating point with no decimal places, kilometers, and then I format that with the height I pulled out of the file. So now I've labeled it with the height from the file. If for some reason the NAM put something out other than 2 meter temperature, we'll be ready for it. So there's that. And then plotting it up. And so while I was sitting here, I got super motivated and played with the grid lines a little bit more. So in addition to turning on the grid lines, which by default turns on major grid lines, I also said for the minor tick marks on the x-axis, I would like you to make them dash dotted lines, which at least on my screen showed up the best here. And I make them black instead of gray. Just really wanted to, so they stand out a little bit. Set the X label, set the Y label, tell it to use the Unicode character for degree Fahrenheit when I label it. And then here's the last part where I use that hour locator. So I set the major locator to tick the days. And for the minor locator, I can give it a list. I use the hour locator and give it a particular list of hours I want it to include. In this case, I want it to tick on the 12 hours. We could say 6, 12, and 18 if we wanted them every 6 hours. Notice I leave out 0 so that it stands out on its own with the day. I probably should invert this and leave the hours as light gray and make the day stand out, but we could change it up here, in fact. Just change that to major. Oh. And then we can go. Just tell it to turn on the minor grid lines for X. There you go. Now the days are ticked more standing out. And we leave the hours just gray lines. But it's here that we say, okay, 6, 12, and 18, we want to tick those as minor ones. If we put all the hours in here, then you end up with them overlaid with the day lines. So we're telling it to skip 0Z here. And then I just left the formatter as it was. So quite a bit more code than we had before, but if you really want to customize the heck out of your plots, you can just keep drilling down here. Any quick questions about this while John gets set up here?
So you have this height above ground 1. Now, these kind of strange coordinates can change from day to day, right?
They can, at least when you're getting data from this, originally came from a Threads data server, so yes.
Yeah.
How do you really do it? I'll hint it here. So if you look at the coordinates attribute, it's noted there. So we could use Python string parsing and split this on white space and get the name of this and then look it up and continue on. That's where Xarray really comes in. And hopefully in another year, we're not doing this by hand, but we're just leveraging Xarray better. But not today.
Can I use the same link?
It's actually a different link. Or, no, I sent you an invite, but you need the link, don't you?
Yeah.
It should be coming in.
Okay, there it is. Yes, we want to join.
Plug it in first.
Before I here, yeah.
Click the yellow tabs? No. Yeah.
Okay, you have the screen now?
Yeah.
Okay. All right, so everybody's excited to do SKUTs. It's 4:30. Yeah, it's my favorite meteorological plot, so get excited about SKUTs. All right, so before we do SKUTs, I want to show you two things that are handy. First of all, Ryan showed you the Metpy doc page earlier. There's a lot of information on here. It's linked on the workshop website, so you should go digging through. For example, if you go to the Metpy examples, there's this gallery of all these pretty maps and things that you can do. If you click on one, it shows you all of the code, how to do it, the output. You can download the files here. Another handy thing is the Metpy API page. So for example, we're going to be doing something with SKUTs, which is in plots. So I click on there. I click on SKUT. And here's some documentation about how we use it, similar to what you get if you did the question mark in the notebook. And it shows you all the examples that we have that use that particular function. Where this comes in really handy is if you're looking at something like the constants, and we have a nice table formatted here. It's what you saw when you did question mark in the notebook, but rendered in a little bit prettier way. The other thing to look for is if you go to the Unidata homepage, up here under news, there's a Unidata developers blog. And beginning, hopefully, next week, we are going to have a post every Monday about how to do something with Metpy. It'll be a combination of videos and blog posts. The idea is to keep them in under 10-minute chunks. So Monday morning, you can open it up and while you're drinking your coffee, learn about how to do some neat little example with Metpy or a tipper trick that you probably didn't know.
Metpy or even just Python for something applicable in our area.
Right. Okay, on to SKUTs. So if you are back in the notebooks directory, where we have all the different lessons, we're going to be working in the aptly named SKUT subdirectory. And there are two notebooks in here, one that you'll do your exercises in, one that I'm going to be teaching from and that you can follow along with. So we'll go ahead and open that one. And what I want to do is this notebook has already been run and it has all the outputs But let's go ahead and clear all of that so we're all on the same page and we can watch as we run. So if we go to cell, current outputs, and clear up here in the menu, or all outputs, either one of these is fine. Clear. You can see now it's like none of these have ever run and the output's not there. It'll be a little bit easier to follow along with. Now, how many people have plotted SKUTs from raw data before? Yeah. And you're used to seeing something like, let me zoom out so that format's a little bit better. Used to getting some text file that looks like this, right? You have to parse that yourself, which is great until there's something that's not formatted right, or there's a weird header or a weird footer, and things go sideways very quickly. There are a couple of great places to get that. So there's the Wyoming archive, there's the Iowa State archive, and traditionally you go there and download, do some kind of query, download your data. But you don't have to do that now because we've built in Metpy ways to go grab data from those, bring it into Python as something that looks like a netcdf file. It's not really a netcdf file, but as you'll see, you interact with it just like one. So let's start by grabbing some data. Make that a little bit bigger for folks in the back. All right. So we're going to import the datetime object. That's how we're going to tell it when we want our sounding. And then in Metpy, we have the IO submodule, which has this function get upper air data that lets you download upper air observations. So here we create a datetime object. So this is a special sounding 21Z from 2010. And then we call get upper air data with that datetime object and then the station. So this will be a Norman sounding. We run that cell and you see it successfully ran. We didn't get anything back. So now we have in that data set DS, if we look at the list of variables, pressure, temperature, dew point, UNV wind, speed, and direction. And yes, UNV wind and speed and direction are redundant, but we can get those for basically free when we read this in. So it saves you the step of having to do that computation yourself if you want to do something like plot wind barbs and then color them or something like that. Then just like Ryan was showing you earlier with his netcdf tutorial, we're going to ds.variables, grab the variables that we're going to use to make this plot, and use an empty slice to actually get the NumPy array back out instead of a variable object. So if we run that cell, I'm going to insert a cell below. So if I show what's in P, you see we have an array of pressures, for example. So now what I'd like you to do is open up this upper air SKUT log P exercises notebook in the same directory. And here under exercise 1, you see I've kind of give you a skeleton of what to do here. Gone ahead and done the imports for you. But grab some data for a sounding that you're interested in. It could be today's sounding from the most recent station or the nearest station, whatever sounding you like, your favorite event. Go ahead and grab some data and get those out as pressure, temperature, dew point, and the UNV wind components.
In your example, you saw the sample for a particular location. How do you know the list of the stations?
So what you can do is if you go to this University of Wyoming archive link, there is a map on their page that has all of the 3-letter station codes.
Trying to get upper data, it's that automatically pull from Wyoming?
That is the default. And then you can specify, in fact, I'll do an Iowa State poll here just for fun.
When I just changed the date for the normal, it gave me an error.
Did you change the hour? Because that was a special sounding. That was a 21Z sounding. So there's probably not many.
No, I did not. No, I didn't. See if I did it right.
You get some data? Okay, good. And put your green stickies up when you've got your data and it's pulled out as variables. If you're stuck, take a look up here. I'm just about done. So if I look at the doc string for get upper arrow data, so I do get upper arrow data question mark, see it has time, site ID, things we were expecting. And then there's this optional argument source, which is by default Wyoming, like he was pointing out. But if you read on down, it says the source of the data can be Wyoming or Iowa State. Defaults to Wyoming. So in my example here, I went ahead and pulled data from Iowa State. Work on this for about another minute or two, and we'll move on. Okay, so everybody's got some data now. This is pretty much like what we did in the main notebook. And as we go on, you'll plot your own SQT for this data. Okay, so if I go back to the notebook here, we're going to use some basic Matplotlib. So I'm going to go ahead and import Matplotlib and use the Matplotlib inline magic command that Ryan showed. So the plots show up in the notebook. And this is the naive skew-t that's really not a skew-t or a log p. This is just a simple plot, linear axes with temperature and pressure. And that looks awful. That looks nothing like what we want to look at for any kind of thermodynamic diagram. As it turns out, if you try to make your own skew-t, you say, okay, I'm going to skew these isotherms over at 45 or 30 degrees or whatever you'd like to, and I'm going to make that work with a logarithm on the y-axis. It gets really nasty really fast, as a lot of people found out. And that's why we implemented it in Metpy. In Metpy, in the plot submodule, there is this skew-t class. Import that. We'll create a new figure. So plot.figure. This is kind of breaking up the command that Ryan used that did a figure and axes in one swoop here. I'm just making a figure. It's going to be a 10 by 10 inch, ideally, figure. And I'm going to create an instance of this skew-t object that uses that figure. So this is going to transform that figure into skew-t, and we'll store it as skew. Now you interact with that skew like you would a normal axis. So we would call ax.plot. Here we're going to call skew.plot. And pressure, temperature, even though that's yx, that's normally how we would think of it as pressure, temperature. We're measuring the temperature. So PT, and then specify that I want that to be red. Plot TD, specify I want that to be green. And Brent, did you talk about the tab, what that means?
No, I did not.
All right. So you can, instead of having tab colon red and tab colon green, you can use plain red and green. And those will be full on 00FF00 values, really bright red and green. Tab is a subset of colors based on the Tableau 20 colors. They're very pleasing. They're more colorblind safe. They're not quite as harsh. When you look at them, they project nicely. So it's nice to go ahead and use those colors when you can. Though red and green, there's really no very colorblind safe form. But then we can add barbs. U.plot_barbs. Here we give it pressure levels that the wind barbs are to be at and the U and V components. And then we'll just set some axis limits. There are some defaults, but here I'm going to set something that makes this particular skew-t look a little better. So we're going to go from 1,000 to 100 millibars, minus 40 to 60 C. And if I run that cell, by default, zoom out on that a little bit, we get something that looks a lot more like the skew-t that we want to look at or publish in our paper. Notice, though, how many wind barbs there are here. That could get annoying. We're working on a way to more intelligently downsample those that maintains the mandatory levels and does some intelligent way. But for now, we can use some of the fancy indexing that Ryan showed us earlier. Let's say we wanted to plot every third, right? So : : 3. We have to do that on the pressure, the U, and the V components. And now every third wind barb is plotted. That looks a lot cleaner already. So take what we've just done and plot your skew-t that you selected in the examples notebook. You can get as fancy as you want. You can downsample the wind barbs, make dotted lines, change the colors. We'll take about 5 minutes.
Where is this colon 3 going?
Where is what?
The colon 3.
Oh, yes. After the P, U, and V in plot barbs.
Makes
So if you do want to, call upon create a certain feature of data, could you just do 2 plots in the data? So you want to plot the temperature and do from the first to the fifth without changing your plot location, plot everything on top of it with just the names.
So that's actually what's happening. Because we're only doing the colon 3 in the call to the plot bars.
Okay.
So we're still using the full P.
Got it. Okay.
Right, so I tried to do something like this to skip. So then ask him, do I use skip, V skip? I need a refresher too.
Or you just so basically display the output of the last.
Well, it's working, and then I can enter.
Sit there, that's okay, it's just time down, hit it again. It really does return 503.
Good.
Or
So yeah, if your problem's hitting the Wyoming data server, either try Iowa or just try Wyoming again. They were having problems last week. Somebody was hitting them over 1 million times a day, and their server was getting crippled. Sounds like that might be happening again.
Oh no. At least it returns to 503 now. It was an HTTP error, not something like, you don't have enough fields.
I can mark that as test. Got a question.
Oh, nice.
So you can play with adding some, for example, I added some line width arguments to make the lines a little bit thicker. Decided they were a little bit too thin for my liking. Horribly boring sounding, I think.
So when you specify color 0.7,
Mhm.
does it mean 0.7 of $256 or?
Yes, it's a black to white scale.
Your results from Iowa State.
Oh, yeah. Okay, did anybody have problems getting a plot of their data? No? Hopefully you picked a more interesting sound. This one from Birmingham is not very intriguing from this morning. Okay, so next thing we might want to do is do some thermodynamic calculations. We might want to find some important levels, the LCL, the LFC, EL. Before someone asks, no, we don't have K percent. They're coming very soon. As it turns out, they're tricky to implement. There's so many different ways to calculate them. Coming up with some kind of sane API for you to interact with is proving to be a challenge, but hopefully we'll have those done over the summer. But for now, what we're going to do is look at the LCL and the LFC. These live in metpy.calc. So we're going to import metpy.calc as mpcalc, like we've done in the past. Let's go ahead and look at what LCL needs. So we're going to do mpcalc LCL. All right, so it wants pressure, temperature, and dew point, and it wants those as the starting atmospheric pressure, temperature, and dew point. So we'll give it a surface parcel. All right, well, that's straightforward enough. So the 0th element of pressure, temperature, and dew point. And it returns, if we look at the bottom of the doc string, there we go. It returns the pressure and temperature. So I assigned them to LCL pressure and LCL temperature. The LFC wants the full pressure, temperature, dew point paths. So mpcalc, LFC, TTTD, assign those to LFC pressure and temperature. And then I'm going to go ahead and plot those. There's a Matplotlib command, AX H line, that plots a horizontal line, so a line of constant Y value. We've modified that so it works nicely with skew T. So skew.ax.axh line. We want it at the LCL pressure. I'll make that a black line. At the LFC pressure, I'll make it a gray line. So 0.7 is from white to black. And notice I have these inside some if statements. The reason being, not every sounding we get, we're going to get a valid LCL or LFC for. So I say if there is an LCL pressure, if it's not none, or LCL or LFC, then we're going to go ahead and plot it. And then I call fig again because we're plotting these on a figure that we've already shown up there once. So by calling fig, it's going to plot those and then show the figure to us again. So if we run that cell, we see our LFC and LCL as horizontal lines on that figure. Another thing we might want to do is calculate the parcel path, the idealized parcel path. In metpy.calc, we have the parcel profile function. It takes the pressure and then the temperature and dew point of the starting parcel. So in this case, we'll use the surface. And then we want to get it in degrees centigrade. So it will plot with everything else on our plot. So this is our call. And then .2 deg C. And if we look at what's in there, we see it's just a bunch of temperatures that have deg C attached. So I can plot that just like I would the temperature or the dew point. So skew.plot P, parcel path. I'm going to make it a black line, or if you wanted to, I think on the SBC it's a blue line, right? So we can make that blue. And then show the figure. So there's your idealized parcel path. Right, so go back to the example notebook, and on your sounding, calculate your LCL, LFC, if you have one, and plot the idealized parcel path for your data.
I said Cape's hard.
Because if the pressure will be
Pick orange and purple to be obnoxious. An amazingly boring sounding. Isn't it wonderful?
Jesus, it's practically driving back.
Yeah.
Where'd you pick that from?
It's Birmingham this morning. Better hope there's no fire.
You need them 80 bats on there. I know we're getting there.
All right, are we about ready to go on? Don't want to keep you too late today. Okay, so for my sounding, did basically just what we've done. I use NP Calc LCL and LFC. As it turns out, I have both an LCL and LFC on the sounding. So I just plotted them and I did it in orange and purple just to be obnoxious in terms of the figure, which now looks like that. They stand out very nice on the projector though. Okay. Now we need to dress up the sounding some. Most of the time when you get those big sheets of paper, you have to plot it by hand. You've got dry bats, moist bats, mixing ratio lines, all these wonderful things on there for you to do some hand analysis. And again, writing those functions yourself in Python and then calling skew.plot on a range of adiabats to plot them is a pain. So we've made that easy with these special line or fiducial line helpers. Scroll it up for folks in the back there. Now you can just skew dot plot dry adiabats, moist adiabats, and mixing lines. And Metpy will use some sensible defaults on the range and plot all of those special lines for you. So we've got our adiabats, there's our mixing lines.
Can you scroll up a little bit?
Mhm.
Why is there that sort of hanging wind bar that's just above the?
That is a difficult problem to solve, as it turns out, when you're messing with the axes as much as we are to get SKUT going. We do have it in our bug tracker to try to solve that, and hopefully also solve it at the same time as we make better downsampling here. You can mask it, yeah. So you could say, don't plot any wind bar above 100 or below 100. Yes.
Yeah. The key is to be able to do it flexibly so that someone doing stratospheric stuff can get their wind barbs up to 50 millibars.
Right. There are several problems like that that lie in here that we can solve the 80% case pretty easily, but making sure that it doesn't break somebody else's workflow is difficult. The other things that I could think of when we were trying to add things to help make SKUT life easier for you was shading areas of cape and sim. Though we can't calculate the numerical values yet, we can go ahead and shade those. So we need to pass shade sin and shade cape, the pressure, temperature, and the parcel path that we've calculated. So again, you could calculate any arbitrary parcel path you wanted. We didn't want to lock you into our favorite surface-based parcel. If you want to use a mixed layer parcel, that's fine. And you get a plot with those areas shaded. So positive and negative areas. You'll notice, again, that there's a little bit of a gap in some of these shadings. As it turns out, there's not a data point exactly where those cross, so Matplotlib can't shade effectively down to there. That is a bug in Matplotlib that they have fixed, and we're waiting on 2.1 to come out. That'll make that go away for us. Okay, so any questions on adding shading or special lines? One other thing we can do is, since these isotherms are skewed over, as the name SKUT implies, we modified AXV line, which, like AXH line, normally makes a vertical line on a plot in Matplotlib. If we want to mark the freezing 0C isotherm, we've modified that where it goes ahead and skews it properly for you. So here I've got the cyan dashed thick 0C isotherm. Okay, the last thing that I want to show you is adding a hodograph. It's a pretty useful plot. It's not a horribly difficult plot to make, but as it turns out, we got to do a little bit of magic to set it in the axes so we have it all in one figure and that kind of thing. So in Metpy.plots, we have the Hodograph class, much like we had the SKUT class. And then from the Matplotlib toolkits, we have to get this inset locator and inset axes method. What that's going to do is allow us to make a subplot and inset it inside another plot. You'll see what that looks like in just a second. So we go ahead and grab the wind speed out of our data set. We didn't do that earlier. And then we add this inset axes. So on skew.ax, our SKUT axes, we're going to make an inset plot that's 30% of the width and 30% of the height of our full plot. We're going to locate it in the upper right corner. Instead of loc 1, you could put upper right. And then we're going to pad around it by 3 pixels to shift it in a little bit so it's not right on the edge. And we're going to call that ax_hod. Like with SKUT, We need to pass the Hodograph class an axes that's going to act on. I want to say that we're going to have a range of 100. Grab a handle to that and call it H. We can add a grid, so those polar rings. Here we can set the increment to 20. And then we'll plot the data. So here's a way to do the masking that you were talking about earlier. So we're going to mask everything greater than 100 for this. Remember, we have to attach units for these comparisons to work. So units.mbar or HPA, whichever your favorite is. We could plot this as a plain line plot, or there's a helper that's plot color mapped. So it will make each line segment the proper color for what the wind speed is at that height. So I pass it the U and V components with my mask that I created, and then the wind speed for the color with my mask that I created. And that's the result. So we have an inset plot, 30% the width, 30% the height, added in, and then we have this colored line using, in this case, the default Matplotlib color map, which is now Virdis. It's this wonderful linear color map that goes from dark blues up to the brighter yellow colors. And you see our rings every 20 with a range of 100. Any questions on Hodographs? We tried to make this as easy as we could because plotting SKUTs is a pain. And it's still a lot of code, as you can see. So this is putting everything together above into one step. So we have all of our imports. We get the data, pull out the variables, calculate all of our thermodynamic variables, and then we make the fanciest plot we possibly can. So that one block of code would make that for you, which is still, turn line number, it's still 70 lines, but it's certainly a lot shorter than if you try to do all the axes transformations yourself. So the last exercise was going to be to dress up your SKUT as much as you want. You're welcome to do that, and we'll stay and help you. If you have to go somewhere at 5, I know that's when we promised we would be done by. That's fine as well. But have a couple of administrative things. So on the workshop webpage, if you refresh it, Ryan has been updating it while I've been talking. There is a survey here under feedback. We'll definitely ask that you fill it out before we're done with the workshop. But you can take it as many times as you want. So if you want to give us some feedback there today, that's fine. But your sticky notes are going to be repurposed. So if you wrote on one of your sticky notes, that's fine. We'll come give you more if you lost them or whatever. But what we'd like you to do is, before you leave, on your way out, you can just leave them on this front desk. Tell us something that was good, that you liked, that you found helpful, and tell us something that was not so good, something we can do to make the workshop better, something that you're expecting to hear and didn't. Be as harsh as you want, we can take it. And we take these and we try to incorporate the feedback that we get before the next workshop. And in some cases, we've been able to incorporate it overnight because programmers don't sleep before the second day of the workshop. And on your way out, once you give us these, we will give you fancy Metpy stickers, or you can grab any of these other stickers you want up here to decorate your laptop. So thanks. Someone's gonna get my stickers out.